then I'm still paying you. I got the hard ass beats like the crack of the tech. Still paying dues. Think y'all forgot what rap sounded like? I'm still paying dues. Back to match up beats, the bang of the average. Still paying dues. I'ma make y'all pay for the dues.
All right, then round of applause for DJ Cash. Glad you make it a little late.
Yeah, I was busy getting money.
Again, like, yes, your money. I understand you want money a lot, but like, focus on databases, focus on your DJ skills, not just like trying to raise money. All right, we have a lot to cover, so I want to get through everything. So today, again, before we jump into course material, again, reminder that homework 2 and project 1 are out, and they're both going to be due in the coming weeks. So homework 2 will be due this upcoming Sunday. Let me turn on the lights, sorry. Yeah, homework 2 will be due this Sunday coming up, and then project 1 will be due the following week. Those days don't match up, 21st, 29th. Whatever the Sundays are, go by the Sundays. The recitation for project 1 will be tomorrow night over Zoom. Go check on Piazza. And again, this will be a recorded session over Zoom, but if you have questions and you want live answers, we encourage you to join and ask them. And again, this is not like you shouldn't ask basic things like, how do I compile my C++ code? It should be like, I've started the project and I want to understand a bit more about what this component means, or what does this file means, what does this class means. Okay? So again, don't treat this as like teaching you, here's how to start at the very beginning of the project. More like, we'll give you some high-level overview of what the ARC algorithm is. We'll go over that in more detail than I did in class, and some other parts of the system. But then if you have more detailed questions about the implementation, this is the opportunity to do that, okay? It'll be recorded, and we'll post it on the slides on Box later that evening, okay? That's tomorrow night over Zoom, not anywhere in person. For the upcoming database talks, as I said last class, today and tomorrow are our visit day from all our industry friends. So we have 3 sessions in the morning tomorrow, starting at 9:30. Everything will be in the Gates building. So you can see here again, I know we asked you to select what companies you wanted to go visit. That wasn't like a contract you're saying, I'm going to meet this company at this time. It was more like we want to know what your preferences and your availability was. So then we ran this through a stable marriage algorithm, optimizer algorithm, and it generated the optimal schedule that tries to meet the most people's requests and demands. Okay? There was one big announcement last Wednesday when we had class. So actually, while we were presenting in class, one of these companies got acquired. Anybody know which one it was? What's that? PinCap, no. The guy actually speaking, Jojo from SingleStore, while he was talking, his company got acquired by Vector Capital. So as he said, SingleStore has been around for a while. It was originally called MemSQL. That's first how I met these guys in like 2012, 2011. We can talk a little offline what the initial incarnation of MemSQL looked like. They had one very, very famous investor who turned out to, who did pretty well last week's announcement. And that is Ashton Kutcher. Believe it or not, Ashton Kutcher was an early investor in MemSQL, or now SingleStore. I don't know how they met him. I don't know how Ashton Kutcher even knows anything about databases. But this tweet is real from 10 years ago. All right? So yeah, congrats to those guys. Although none of them were there anymore, right? Eric Finkel left. Nikita, I mentioned, he left SingleStore and went to Neon that got bought by Databricks for $1 billion. So whatever, they're fine. All right, so last class, we talked about an alternative to the tuple-oriented storage we saw before with slotted pages. And we said, like, it isn't the only way you have to store data, right? Store tuples in pages. And we looked at mostly the log structured storage scheme, where instead of actually storing maybe the entire tuple, and every time it gets updated, overwriting the existing tuple, we're just appending to these log files that get written out to disk. And then in the background, there's some compaction mechanism. We talked about level compaction or universal compaction to combine them together to reduce redundant information and compress the sizes. Index organized storage, the idea was it looks basically like the slotted page approach, But instead of having this heap file where I'm jumping to unordered pages to find the data I'm looking for, I'm actually going to use a tree-based data structure, like a B+ tree, which we'll discuss in a few weeks, and traverse down to the tree to find the data I'm looking for. And then in the leaf nodes, rather than being a pointer to where the data exists in a heap page, it's actually the data itself, right? MySQL InnoDB does this, SQLite does this, right? And has, again, each of these approaches have pros and cons. But ideally, we saw that they were better for doing update-heavy or write-heavy workloads where you're ingesting a lot of new information from the outside world, right? Most of the queries that exist in the real world, though, are not going to be write queries. Most of the queries are going to be read queries or select queries. And in fact, for certain read queries that are maybe looking at a lot of data or trying to do more complex things, these approaches are actually going to be terrible, right? Even the heap file, the tuple-oriented storage we talked about before, the slotted pages, that's going to be terrible for analytical queries. And the SingleStore talk that he gave last class is actually the introduction for this class, today's lecture, because a lot of things he was saying maybe didn't make any sense of why you want to use a column store. That's what we're going to talk about today. So I'm going to briefly go over, again, what the SingleStore guy talked about last class and talk about the different types of workloads that are out there for databases and what we, and how we can see how we can design our database system to account for these design decisions or these workloads and come up with more optimal schemes. And then the beauty of SQL and the relational model with the separation between the logical layer and the physical layer is that I can still expose a relational table interface to the application. Like I'll call create table and I'll write my SQL queries on that. But underneath the covers, we can use one of these alternative storage models to come up with a more optimized scheme for our data to make queries run faster. And not just a little bit faster, I mean like orders of magnitude faster. I mean, think of going like, in the early days of column stores, I had a friend who worked at one of the ones called Vertica. And he told me that there was some Australian telephone company, they had queries that would take days. And then when they switched over to a column store system, which we'll talk about today, it went to like minutes. And their minds were blown. And we'll see why that's the case here. So we'll go talk about different storage models, and then we'll talk about techniques to actually make this run even faster by compressing the data. So this is a bit of a repeat of what, again, the SingleStore guy talked about again, but I want to put it in my own words. There's roughly 3 categories of database workloads. There's OLTP, OLAP, and the last one is HTAP, hybrid transaction processing. OLTP is what people typically start with when they're building a brand new application. Like if you're a brand new startup, you don't have any data. You're going to build some kind of app that people can connect to, interact with, and then you'll be ingesting new data from updates from the outside world. That's an OLTP application. Right, you're taking new data from the outside world, but the amount of data that you're taking for every single operation, for every single query, is going to be small. Like think of like posting a message on Reddit, a comment on Reddit, like you typing in the box and hitting send. The amount of data they're storing for that one comment request is actually not that big. Like your username, a timestamp, and then the text field. Or think of like buying something on Amazon. You put something in your cart that updates the database. It's like your user account information, a timestamp, the item you want to buy, and then the quantity. Right? It's not that much data. But we're going to do a lot of this, and we want to try this very, very quickly. OLAP is once you have a lot of data, or existing data, then you want to run analytical operations on them, basically asking questions about that data to extract new knowledge based on the aggregate data that you have. So going back to the Amazon example, OLTP would be like, again, someone buying one item, right? For every person buying one item, that's a small amount of data per person. But the total amount of data that they're generating across all the orders, across all people using Amazon, is actually quite a lot. So then now when you want to run analytical queries, you can answer questions like, what's the number one item bought in the city of Pittsburgh on this day in September when the temperature was above this degree or that degree, so forth. Right, that's an analytical query because you're asking a question about looking across multiple entities or multiple entries in the database, in the tables. And so these queries are going to be more complex than we do in OLTP. Right, we're joining multiple tables, doing window function aggregations, all the kind of stuff you did in homework 1. You typically see them in the OLAP workloads. HTAP, or hybrid transaction analytical processing, this is like the holy grail for systems, but it doesn't always pan out, where you want to be able to do fast transactions or do fast OLTP operations. You can ingest new data very quickly, but then you also want to ask questions about that data where it exists in that database without slowing down the rest of the workload. SingleStore is trying to push this. PinCap-TidyB is another one to do this. This one can be a bit hit or miss because oftentimes it isn't the best OLTP system and it isn't the best OLAP system. And if you're like in a big company, the people that care about OLTP, they want the best ones, they'll pick something else. And the people that want the best OLAP system, they'll pick something else. Right, but this is a market segment that does exist. AI is kind of separate from this, and it's kind of what comes after OLAP. So OLAP will ask you can ask questions about what was this, what was that, based on the data you have. The AI stuff that's starting to come out is starting to ask questions about why things were a certain way. Like why was this item the number one bought item in Pittsburgh at this date and time, right? And what aspects of it make it interesting for people at a certain demographic and so forth. Those are the kind of things AI cares about, and we'll see how we handle that later on when we talk about vector indexes. But it smells enough like OLAP that we don't have to show it as a separate category here. So a really simple quad chart to understand the distinction between these two sort of categories of workloads is looking at whether the workload is write-heavy versus read-heavy, and whether the operation, the query that you're trying to execute in the database system is going to be simple or complex. And complexity is not really a scientific term or something we can measure a query in based on. It's usually something like, how many tables does it join? Does it do aggregations? How many group bys? How many nested queries? Right? In OLTP queries, they're pretty simple, like select star from table users where username equals Andy. You're going to get like one thing doing a lookup on an index. So you can roughly divide the workloads like this. So on one end, on the bottom corner, you have OLTP. These workloads are considerably more write-heavy than OLAP, because again, you're ingesting new data from the outside world. Although most of the times, even in an OLTP system, most of the operations are read queries. And then the queries you're actually running are pretty simple. Like go select Andy's record, bank account information, go get Andy's orders from the last year. OLAP is the other end up here, and the workloads are they're typically almost always more read heavy, and the queries are more complex. So OLAP OLTP is an older term. It goes back to like the 80s. OLAP came out of the 90s. It was actually invented by this very famous database researcher called Jim Gray. He won the Turing Award for databases in the 1990s. He invented a lot of stuff we're going to talk about in this class, like two-phase locking and other techniques as we go along. He famously got lost at sea in 2006 when he was sailing his boat in the San Francisco Bay. And he was so famous, they actually moved satellites to go back over the San Francisco Bay to actually look for his body or his ship, and they never found him. So he was considered lost at sea. Truth is, though, when he invented this OLAP term, he was actually doing it on the behest of another company that was trying to sell a new product and say, hey, look, here's this brand new category of systems called OLAP. So he wrote a paper like, hey, look, there's this thing called OLAP. This is why it matters. And then when people found out he got paid to write the article, he got retracted. Other than that little snafu, I never met him. He was considered a good guy, though. All right, and then HChat would be somewhere here in the middle, right? Again, this is not a scientific chart. This is trying to say, like, again, how to roughly think about the different workloads. So for today's class, we're going to use an example actually from Wikipedia. So this is actually based on the Wikipedia schema. It's open source. It's written in PHP. They run off MySQL. It's one of the largest MySQL clusters, I think, around. Actually, they might have switched to MariaDB by now when Oracle bought them. But this is roughly what the schema looks like. So we're going to have a user account table. Again, that's your login information. We'll have articles or pages for that define, like, here's an article on Star Wars or whatever. And then we'll have a revisions table where we're going to put all the new versions of the pages that come along, right? Or new versions of an article, all right? And what I'm showing here is actually the content is inside of this table here, the revisions. And actually, the real schema, they put it as a separate table, right? Because they don't want to have a giant blob in the page itself. But we can ignore that. But you can see here, there's foreign key references all around. Wikipedia is a sore subject for me because a few years ago, somebody actually wrote a Wikipedia article about me. But then they put this line in that I used to have in my bio somewhere. It said, I was born and raised in the streets of Baltimore, which is true. I was born in Baltimore, but obviously not in the streets. And then Wikipedia they flagged that and says, in the streets, it's not scientific or encyclopedic enough. And then it got flagged, or again, it got taken down. And then whatever. And then since then, I get emails basically every 3 months from like these scammers saying like, hey, give us money, we'll write your article for you, right? All right, so if anybody's watching this, was I born in Baltimore? Yes. Was I born in the streets of Baltimore? No. Right? That should go without saying. Okay. Yes.
Why are we trying to separate OLAP and OTP? Is that segregation of queries or database?
The question is, why are we making a distinction right now between OLAP and OTP? At this point, I'm only contrasting the workloads, and then we'll see how we'll design a system for those different workloads. And then at the end of the class, we'll finish up and say, okay, well, do I have separate systems? And how do I get data from one to the other? Or can I have a single system handle both? So we'll cover that. I think that'll answer your question. Other questions? Other than me being from Baltimore. Okay. So again, I said at the beginning, the relational model is beautiful because it says, hey, this is what the data should look like, how to represent it at a high level. It doesn't say anything about how we actually store and represent that data as physical bits or bytes we're going to store on the underlying storage medium, right? So there's nothing about the relational model that says just because you declare a table and a table has these attributes, that those attributes have to be stored contiguously on a disk page or in memory. In fact, we already saw that we could break that notion when we had the oversized values, right? We talked about the toast table or the external storage for like in Postgres. Like if I have a really large text field, I don't store that in my slotted page. I have a separate page where I store that and then store a pointer to it. And then now when I run queries on it, underneath the covers, the data set is going to stitch that tuple back together by following the pointer. But use the application, you don't know that things have been separated. So it turns out for some workloads, particularly OLAP workloads, storing things contiguously is actually going to be not the best way to do it. So for OLTP, as I said, the queries are simple and they're accessing a small amount of data. And this is what people normally build when they first build a new application. Like if you're a new startup or whatever, new project, this is what you end up building. So here's three sort of simple examples of OLTP queries in the Wikipedia. So one is go and get the latest revision for a given page by looking about the page ID. So there'll be an index on page ID because if it's the primary key, right? There'll be an index on that, and we can do a lookup. Another one is someone actually logs in, so we'll update the last login timestamp with the current timestamp, whatever host name they use to log in, and again we'll do a lookup based on the user ID. So again, that'll be another index lookup. That's very fast. And the last one is like inserting a new entry into the revisions table, right? So if we store things contiguously for a single tuple, well, most of these queries, all these queries here are touching well, the bottom two are touching one tuple. The top one can touch at least two tuples because whatever the current page is, or for a given page, and then whatever the latest revision is. An OLAP query looks something like this, where I'm trying to get the count the number of times someone has logged in logged into the service, where their host name ended with the .gov IP address or namespace, right? This is actually an example from a real scandal 15 years ago, where a bunch of Congress people were having their staff who were on government salaries log into Wikipedia and update the entry for the congressperson saying like, look how great they are, or here's them doing charity work, right? So you're basically paying government employees to go put out propaganda on Wikipedia. So you could use this query. This is basically roughly the query they did to find it. So in this example here, again, we're not looking at a single record. We're not looking at one person logging in. We're looking at all the entries of logins to try to find a match here, right? So there's a bunch of people got busted for this. Joe Biden did this. Mike Pence got busted for this, right? Basically, all of them are doing it. So the thing we haven't talked about yet is the storage model, which again is a way we're going to physically represent data that's in our database in tables. And it's basically going to tell us how we're going to organize things either in memory or on disk. And as I said, that based on the workload, the different storage models we could use, it's going to have wildly different performance because it's going to depend on what the data is actually needed and how it's going to be used by the query. So there's two basic approaches: the n-area storage model or the row storage. This is probably what we're most familiar with, and this is what we'll be seeing in our examples. And then the column store one is the one we've been alluding to. We're going to store things instead of a row-based, we'll store it as a column-based. We'll see why that matters. And then the last one, this hybrid storage model, or also known as PACS, this is the way most systems actually implement their column stores. So if a system comes out and says, yeah, we're a column store, they don't actually mean the second one, they're gonna mean this third one here. And so I'll explain what that looks like, what the difference is. So the n-area storage model, or NSM, this is the academic term, but if you say I have a row store, this is what they mean, and everyone will understand what you're talking about. This basically says that for a given tuple in our database, in a table, we're going to store all its attributes contiguously within a page, assuming they fit. Right? We have to spill to an overflow page or oversized page. That's a separate issue. The idea is that all the data for a given tuple are stored right next to each other within that page. And then the next tuple that we're going to store on the page doesn't start until we finish whatever the tuple we're writing out the data for, right? And this is going to be great for OLTP workloads because the kind of queries we're going to run are either update queries, where we need to have the whole tuple to update it anyway, or insert, we're just inserting the tuple in its entirety, or our select queries are going to be only accessing one tuple, and oftentimes they need all the data within that tuple. So you want all the attributes. So I'm going to skip this, just go through quickly, but this is basically the slotted page that we stored before. I'm showing this so we see the distinction later on when we talk about the column store. So within our database page, we have our header, then we have the slot array at the top. And again, now as we scan down through the data we want to store up above, right, we're just going to write it from the end to the beginning, and add pointers and offsets for the different locations of the tuples, and we keep going as we scan down over and over again, right? Right. So this is just rehashing from the things we talked about, right? Until you fill it up and then you run out of space. So let's go back to one of these queries on the Wikipedia. So say here I'm trying to get the user information for one account. So this is somebody logging in. So I'm going to pass in the username, and then like a hash password, right? I don't want to store, whenever you see data breaches and they always say like your password got leaked because they store raw passwords unencrypted in the database, don't do that. Do that, all that encryption stuff outside in the application, and then the database just stores the encrypted data, right? But I mean, this is basically the query you would run. So now for this username, I'm going to have some kind of index that I'm going to use to help me find the record ID that I want. Now I'm not going to explain what this index is. That's in 2 weeks when we start talking about indexes. But think of like a hash map or a B+ tree or some data structure says, for a given username, here's the record ID, where to go find it. And then now my database system is going to go look in its page directory and says, okay, well you want record 1, 2, 3, 4. That's on page 5. That's where that's location in my database file. I bring that into memory, and I know how to then use that slot array to jump to the offset that I want. And lo and behold, there's the tuple that I was looking for. Right? And I'm happy. And then now if I want to do an insert, again, same thing. I have some free space map. It says, okay, here's a page that has free data. All I need to do is go make sure that page is in memory, jump to some offset, and just write it out from beginning again. But now let's do that OLAP query before, where we say, give me all the count the number of times people have logged in per month from a .gov hostname. So in this case here, there isn't a lookup on any single predicate I want to, or single primary key or discriminating key. I got to look at all the pages because I don't know where any .gov host names are going to be. So I'm going to scan all the pages, and I'm going to bring them in one by one. Again, this is a row store. So the first thing I got to do is run my where clause, where I say, find me all the host names that end with .gov, right? So I got to look at all these values in here. And then once I find matches, then I got to run my extract clause to convert the last login into the host name, sorry, the month name. So then I can then compute my aggregations. So then I got to look at this data over here. So what's the problem with this data? These are the other 3 attributes. Did this query need it? No. Did we have to read it from disk and put it into memory? Yes. So because this is a row store, whatever is attached to the query, whatever columns, attributes a tuple has, they come along from the right because they're in the page with all the other data that I do need, right? So in this case here, I'm not showing the size of the data, but like you roughly say about over 50% of the data that we needed, 50% of the data for a tuple was actually not needed for this query at all, but I still had to go to disk and go read it. So this is why row stores aren't going to be great for doing analytical queries, because most of the time analytical queries, I don't need all the attributes. You don't see select star queries in analytical queries very often, or analytical workloads, right? You shouldn't run select star anyway, but in general, you don't really see that unless someone's trying to do a bulk export, and even then, there's faster ways to do that than select star. So for the row stores, it can be great for fast inserts, updates, and deletes. It's great for queries that need the entire tuple. I need all the attributes for a small number of tuples. And I can do a bunch of tricks like the index organized storage, all the clustering techniques we'll cover later on to make this go really, really fast. So that I'm only reading the exact single page I need to go get the data that I want. There's other tricks. You can put a bunch of data in the index as well. So maybe I only need to traverse the index, even if I'm not using index organized storage. And all my data is in the index. I don't even need to touch the tuples. We'll cover that later. This is going to be bad for analytical queries because we'll have a lot more pressure in our buffer pool because now we're copying in pages with data that we don't even need for this particular query. So the alternative is the decomposition storage model. Think of like two opposite ends of the spectrum. So the n area or the row storage, like putting all the data for a tuple contiguous to each other. In a decomposition storage model is the academic name, or the column store. We're actually going to split up all the data for each tuple and store their attributes separately. But now we're going to, within our pages, we're just going to have the data for one attribute within the table. All those are going to be contiguous across multiple tuples. So this can be better for analytical queries because if I'm only going to access a small number of the attributes for a given tuple, I don't bring in pages that have data that I don't need. I only get exactly the data that I do need. Of course, now, what's the challenge of this? What's the problem? Faster reads, slow for what? Writes. Because what do I need to do? If I insert a tuple, I have 1,000 columns, and I got to break it up into 1,000 different pieces and write to 1,000 different pages. And again, he was sort of asking about this. We'll see how to handle that later in today's lecture. So let's go back to our example here before. So we're going to store essentially all the data within each column are going to be fixed length values stored in basically simple arrays. So I'm going to take this first column A. I'll have my first page. There'll be some header that says what's in the page. And then I'll have a null bitmap that's going to correspond to all the data within within this column for all the tuples. Right? Remember in the row storage model, every tuple had its own header. Inside that own header, it had its own little bitmap to say whether the values, where certain values are null or not. So now I don't need to store a header per tuple. I just have a header for the single column, and that's enough to account for all the data within this. And I'll do the same thing for the next column, and then the same thing for the next column, right? So we go back now to our example before. So we take our Wikipedia data we had, right, for the login information, the user information. And again, instead of storing it as a row store where all the data is contiguous across the tuple, we're now going to split it up so that all the host name data will be in one page, all the login information will be another page, all the password information will be another page, right? Now they're all separate pages. So now if I run that query before, where again, I'm trying to find all the people logging in with the government host name. So the first thing we need to do is look, okay, I got to run this where clause here, and I need to look up on the host name attribute. So I just go get the one page or the set of pages that had that host name information, go bring that into memory in my buffer pool, and then rip through that and find all my matches. Again, I'm not jumping over data that I don't need. I'm not jumping over username information or the user ID. The pages I'm bringing in only have the host name. So I can do that very efficiently and rip through that very fast. So then I collect what tuples match my predicate, and say, okay, well, the next thing you need to do is run the aggregation, complete the aggregation, and run the extract function. That's on the last login attribute. So I go fetch that page that has that information, and then now I know how to then jump into these different offsets. I'll explain how to do this in a second. to find the data that I know match my host name from the where clause, and then here's all the tuples that I wanted. Yes?
Does this mean that the page size in this can be will be different sizes?
The question is, does this mean the page sizes in this scheme or the storage model will be different per attribute, different per page itself, or what do you mean?
Different, like it's right now in this figure it shows that each column is a different page.
Mm-hmm.
So does that mean each column has one page? So depending on the size of the data or how sparse the data is, the size will be different. Like if one column is a single character and the other column is a double value or a float value, then the size of the page is different.
He's asking, would it be the case that the database page size for an attribute within a table will be different across attributes? No. It'll always be some fixed size. Because it has to be, because we want to put that in our buffer pool. If our buffer pool has 8 kilobyte frames, actually in the OLAT world you want to go bigger, so like 32 megabytes frames. I don't want to have to start figuring out how to pack things in from different page sizes. So in general, these will all be the same page size. Now that means, of course, some attributes will have more pages, and that's fine. Yeah. So how do I do this magic? Going back here, how do I figure out what tuples actually are matching based on the predicate? Well, there's 2 basic ways to do this. One is to use fixed length offsets, where you know that like if I'm scanning through the data and I find matches for my where clause, I keep track of where my offset is in the array. So I'm at offset 2, offset 5, offset 6. So then now when I go look at another attribute, I look at its pages. Again, it's just an array. All the values of fixed length. So I know how to do simple arithmetic to jump to the offset that I want to have the corresponding tuple that matched whatever the previous operation was. The other approach is you actually embed tuple IDs in the columns themselves. So think of like for every single value, I have like a little 8-bit or maybe 16-bit tuple ID, so that then I have some kind of other index that allows me to jump to find the data that I'm looking for. So these can be variable length if they want to do, but these things will always be, I would have an index to map to this. I'm only showing the second one here just as to say, like, you could do this. Somebody did try to do this. Don't do this. This is what Data Allegro did. They basically took ingress in the 2000s, kind of hacked it up, make it look like a column store, but because it was a row store, not a true column store, they had to play this game to make it actually work. And then Microsoft bought them for like $200 million. And then within 3 months, they realized that was a huge waste of money and threw all the code away and started building the parallel data warehouse as a real column store. Actually, that was Jignesh Patel, the other database professor. That was his advisor, Dave DeWitt. Microsoft hired him to go take the guys that were doing this and make it actually be production ready. And he's like, this is total crap. And he told me that you're wasting your money, and they threw it all away, right? So don't do this. I'm just showing you could do this. We want to do this one over here. But now the question is going to be, okay, well, it only works if things are fixed length. For integers, that's fine. Floats, fixed length, fine.
Sorry, why is it so bad to have embedded IDs?
The question is, why is this bad embedded IDs? Because now I have to store an extra number for every single value that I'm actually storing. Then I need to maintain a separate index in my file that says, here's how to jump to, offset 3. Because these things can be whatever arbitrary length that they want to be.
Sorry, if you have an index to know where to jump, why do you need to write the ID?
Because if I'm doing a match, if I'm scanning through, say, column D, and I find a match, I'm scanning through the column, I find a match here. I need to know, okay, well, this is 3, so that when I jump over to column A, I know how to get to the 3. It's allow me to stitch the tuples back together. Don't do this. All right, so again, if we require all the values in our column to be fixed length, how does this work? We have strings. Well, we'll cover more about this in a few more slides, but the trick is we're going to compress the data, convert anything that is variable length to fixed length. So we don't have this problem. So that means any string is going to be converted to a fixed length number, And then we'll have basically a dictionary lookup to say, okay, for this number, what's the original value? So we can store that as an auxiliary data structure on the side. But then as we rip through our columns, we're only looking at integers, and that's going to be way faster. The alternative is you could just pad out the strings. Like if it's a 32 character varchar, just always put a bunch of extra spaces at the end if it's not 32 characters, so it always fits. But that's going to be wasteful as well. Instead, the answer is going to be dictionary compression. Again, we'll cover more about that in a few more slides. So to round out the DSM, to summarize it, all right, the benefit we're going to get is that we're going to avoid wasted I/O because we're only going to get the bare minimum data we actually need to process the query. We're going to bring that in and not bring in any other attributes that we don't care about. The queries themselves are actually going to execute faster because now as we're ripping through the columns, we're kind of just looking at contiguous data like as strides in memory, and that's going to be great for modern CPUs. I know we said we're going to talk about CPUs too much, but like Intel CPUs or modern superscalar CPUs, they don't want any branches, they don't want any jumps. So if I can avoid if clauses, if I have to jump over things, my CPU is going to be way faster because I'm not going to have stalls in my pipeline. So if all my data now is all contiguous and it's all in the same value domain, like I'm just looking at integers, then I can rip through that very quickly. And we'll see how we handle that in lecture 14. Furthermore, I can actually compress the data much better than I can in a row store because now all the data within a page are going to be in the same domain, right? It's going to be like, think of like if I'm recording the temperature for this room, if I just have my data pages just record temperatures, they're a bunch of integers. I can compress the hell out of that way better than I could if like it had integers and strings and floats and a bunch of random stuff. Like it's thinking like trying to compress a JPEG. If you try to run a JPEG through like gzip or whatever, it doesn't do a very good job because it's kind of a bunch of random data that's already been compressed. But if you open a text file and put a bunch of zeros in it and run that through gzip, it's going to compress the hell out of it. That's basically what we're going to get with our column store. Of course, nothing's for free. It's going to be slow for point queries, doing single tuple lookups, because now I got to stitch all the data back together from multiple pages. Insert sub deletes are going to have the same problem, right? Because you basically have to do this stitching and splitting over and over again. Okay? Any questions about column stores? So this is going to be great for, again, if we have queries on tables that are very wide, meaning you have a lot of columns, and I'm only need to touch a bare minimum number of attributes within that table. Best case scenario is an OLAP query that touches one column, right? But truth be told, those kind of queries are not that common. And so at some point, I'm going to have to stitch my tuple back together. And so if my data is completely broken apart across multiple pages, if I break everything up as columns, then even though I may filter out a lot of data during the query, I have 1 billion tuples, but I end up only needing 1,000 tuples, I may have to go get all those 1,000, for each tuple, 1,000 different pages to put that tuple back together. Again, that's if I break everything up as completely as the column store. So what we really want is something that kind of smells like a column store. We get that benefit of not bringing in pages that we don't need, or looking at data that we don't need, and the data that is in the same column or same attribute is close to each other, so we get great compression. But if I have to go get data from the other attributes for that tuple, they're close by, relatively close by, where I can go, I either already fetched them in memory, or it's not a big leap for me to go get them. So this is what the hybrid storage model called PAX supports. So PAX stands for partition attributes across. This was actually, there's a paper came out in 2001. The first author is Natasa Alamaki. She was the database professor here at CMU before I started. And then she left for Switzerland. She's brilliant. She left for Switzerland in 2007, and then I was hired to replace her. So this claims the paper looks like it came from CMU, but this actually wasn't the last chapter of her thesis she did at the University of Wisconsin with Dave DeWitt, the guy who said, I just told you, that told Microsoft they wasted $200 million buying that company. So he was her advisor. He's brilliant. All right, so this approach basically is, the idea is that it's going to look like a column store, but the data that the data for a single tuple is going to be close enough to each other so that I don't have to make a very long. I may have already brought that data into memory, even though I may not need it, all of it. So again, so most systems, when they say they're going to use a column store, almost 99% of the time they're doing this. I can only think of one or two systems that don't do this, but everyone else is doing this. And then these open source file formats like Parquet and Orc that you might be familiar with. And now there's modern versions of these like Nimble from Facebook or Vortex from the SpyroDB guys, where these are all essentially doing this. So if we go back to our diagram here, again, so what we're now going to do, we're going to horizontally partition or horizontally split up the data based on some criteria like the number of tuples or the size of the data. Right? There's some way to say, okay, here's going to be some chunk of data, or sorry, some region of data. And then now we're going to then write them out within that region to be a single column store, sorry, in a columnar format. But again, within that sort of region, all the data for a single tuple will be located close to each other. So when you create this PAX file, you end up writing the header at the end. And we're going to do this because think of like we're trying to generate, a 1 gigabyte file. So I don't actually know what all the data is going to be in before I actually scan it. So I'll keep track of things in memory, and then when I'm finished, I write out the footer that has all this metadata, right? So I'm showing it appearing first. This is actually the last thing you would write when you create one of these files. So the first thing, again, I'll break up the first 3 tuples. I'll put in some chunk. I don't want to call it a block of data. I'm trying to use generic terms. In Parquet, they call them a row group. That's considered the canonical term. Basically, it's just some set of tuples I'm going to put together in a single. I don't want to use the word cluster, in a single region within the file. Again, in Parquet, I think it's like 1 million tuples. In Orc, it's like by default like 100 megs of data. There's different criteria to decide how you partition these things up. So again, within now my row group, I'll have this another header that says here's all the data within it. And then inside of it, you'll see I put all the data for the column A together, all the data for column B together, and all the data from column C. Right? And I'll call these these column pieces within the row group, they're called column chunks. And I'll do the same thing for the next one, right? And each row group is going to have their own, again, metadata, keeps track of like, I'm compressing this way, or here's the dictionary you can use to decompress this data, right? So if you go look at like any presentation from Databricks or Snowflake or other companies, right? When they talk about Parquet organization, it's roughly going to look like this. And they're talking about PAX. Right? Is this clear? So again, don't think of these as in the OLTP world, we talked about like the page sizes. There's always some multiple 4 kilobyte, 8 kilobyte, 16 kilobyte pages. In the OLAT world, I'm reading large amounts of data. So it's usually these things are like organized in the size of like S3 buckets, like 8 megabytes or larger, where I'm trying to get a lot of data all at once. And so even though I'm saying this row group here might be kind of big, much larger than 48 kilobytes, and maybe I'm bringing in data that I don't actually need, it's still going to be a big win if I have to stitch things together. The question is, what goes into deciding what the number of rows in a column chunk? Maybe it's the number of rows in a row group. I said like the default in Parquet is like either Parquet is like 1 million and it's just whatever they picked it, and then I think Orc goes by like data size. So as I'm writing it out, if I wrote out like 100 megs, say, okay, that's it, make a new row group. But you can tweak those. Yes. Yes.
You're doing the same thing over here with the metadata. You have the dictionary encoding as well, right?
Statement is your statement is like the row group metadata is wasteful.
Yeah, like there's certain DLEs, dictionary encodings in all of the cases they might have a lot of repetition, right? So they're essentially doing the same Italian.
The statement is that the metadata across row groups could be repetitive, and therefore you have a lot of wasted data. For dictionaries, yes. But the metadata is not that big compared to the rest of the data. Like if it's a kilobyte and your data is like 100 megabytes, it's nothing. Yes?
So this is facts file organization, not page organization. Like in earlier slides you were showing page
Yeah, good. Okay. So the statement is, and he's correct, this is my fault. So I'm saying this is a PAX file organization. It is not page organization. Yeah, so you could think of like, here's a file, and then within it I have different pages, and those pages will all be sort of fixed length, right? Within the row group, the metadata stuff at the bottom is usually whatever the size is, but you might still organize that in 4 kilobyte pages. But yeah, you can think of like, I'm not defining what the size of the pages are within a column chunk within a row group, but at the end of the day, when it lands on disk, it's still going to be 4 kilobytes, but the database might perceive it as, I think, what, 8 megabytes or 1 megabyte or something like that, like a larger size. It's not, everything is always, you always have split in pages. Yes. But the way typically in a Parquet file systems address it, it would be at the row group level. So then you have to read the row group header, because that's at least going to tell you what the offsets are for the column chunks. So you can do things like, if I only need column A from this row group, I could go read this. That tells me where the starting point is for each row group, and then I could jump to get the header for that row group, and within that, I can then get the offset to the column chunk that I want. You could store that down here, but then that makes this thing kind of bigger. Now we're getting implementation details, but in the case like Parquet, this is implemented as protobuf. And protobuf, you can't deserialize incrementally, you have to deserialize the whole thing. So if I have all my metadata inside this, and this thing's like 10 megabytes, I gotta decompress 10 megs, even though I might only need like 10 bytes out of it. But that's in the weeds. Yes, the newer file formats replace protobuf with flat buffers from Google. That's the right way to do it. Okay. All right, so let's try to plow through compression real quickly. So at the end of the day, the I/O bottleneck for this class here, what we're talking about in this semester, the I/O bottleneck is always be so the I/O cost is always the main bottleneck when we actually want to run queries. In the advanced class, we'll start worrying about cache lines and other things, but for this class, we'll assume it's always disk, right? And especially if you're running in the cloud and the disk is like some box running over the network, that can get slow. And again, that's going to be a problem. So what we want to be able to do is that we want to compress our pages when we write them out to disk, so that when we read them back in compressed form, the amount of useful data we're getting from one I/O increases. So if like a page is uncompressed, I can put 10 tuples in it. But if I can compress it, and I can put 100 tuples in it, now for the same I/O with compressed data, I can get 100 tuples and bring them to memory. Now I have the space for memory to deal with it. In some cases, you actually don't need to decompress it, and we'll see how to handle that. But the main trade-off we're going to face here is sort of classic computer science, where it'd be speed versus or compute versus storage. So I can pay more CPU costs to compress my data and decompress it when I need to access it, in exchange for having a lower storage overhead and lower I/O cost to get data in and out. So the things we're going to want in our compression scheme in our database system is, number one, we have to make sure that our compression scheme always can produce fixed length values, because we need that in order for the offset mechanism to work to address tuples within a column. Because if I'm taking like 32-bit integers and I compress them, and now they're like, some are 16 bits, some are 24 bits, I have no way to know how to jump to offset 1, 2, 3 to find the data that I'm looking for. I got to then use an index, and I don't want to have to do that. So all our data needs to be fixed length. Variable length data, we're going to store as a separate pages or a separate storage pool, and that we can run whatever compression scheme you want on that, and let that be variable length. We don't care about that. Not entirely true, but for our class, yes. Another thing we want to be able to do is postpone when we actually have to decompress data in order to be able to use it or give it back to the user as part of the result of the query. So that means that we want to be able to run queries directly on compressed data and then not have to decompress it to figure out what's actually inside that compressed data. And the last one should be sort of obvious, but that we want to make sure that whatever compression scheme we're using is considered lossless. What does that mean? Like lossy versus lossless, yes?
You can decompress it and get back the
He said, yeah, basically, if you compress data and then you decompress it, I get the exact same data back. I get exact same bits. That's considered a lossless scheme. A lossy scheme would be something like MP4, MP3, right? I could take a video file or a sound file and compress that in such a way that it's not perceptible as humans, either through our eyes or through our ears, because we can't detect whatever, things they're throwing away. But it's not an exact copy of the data we had before. So we don't want to do any lossy compression. We only do lossless. You can do lossy compression on data systems, but this is something a human has to tell us to do. So the example I always like to use is, say I'm recording the temperature in this room at 1 second granularity for an entire year. But maybe a year from now, I don't need to know exactly what is the temperature at this time, this exact moment, this given second. I maybe can bucket the data within 10-minute aggregations. So if I do that and delete the 1 second data, that's a lossy scheme because now I'm throwing away the original data. But for my use case, that might be good enough. So database systems will do lossy compression for you, but you have to tell it you want to do that. There's even other techniques where you can actually keep the data in its original form, but then run lossy algorithms on them to compute queries, called approximate query execution, where you get estimates of things. Sometimes they give you bounds. But again, we'll worry about that later. For this class, this lecture today, we can't lose data. So there's 4 different choices we have to compress things. The first is the block level and the page level, right? We're basically just taking a page of data, and we're going to compress it. The tuple level, we're going to take the entire tuple itself and compress that. And you can only really do this in a column store. The attribute would take a single value within a single column for a single tuple. We'll compress that individually. We saw that before with the overflow pages for like large varchars and text fields. Like Postgres will store in this thing called the toast. It's separate pages that then runs like gzip on that and compresses that, but it's only do that for a single attribute. And the last one's gonna be columnar compression, and then we'll spend most of our time on that. But that will get the biggest win for using DSM or PAX. So pretty much every system today that's using a column store is going to use this bottom one. Some systems will give you the third one. The second one is pretty rare. I know like one system out of China called Terark. They got bought by ByteDance, and the guy was unhappy with having it at ByteDance, and he has a new startup. I forget what it's called, but they can do tuple level compression. His website has him complaining about a parking ticket or something. It's in Chinese. I can't read it, but I can post it on Piazza. And then block level, we'll talk about real quickly. This is rare, but to me, this is interesting too. So for this, we're going to use what I'll call a naive compression scheme or general purpose, where it's pick your off-the-shelf favorite algorithm, gzip, zstandard, LZ4, snappy, whatever. Just take your block of data, run it through the compression scheme, and you get a compressed block out. And it's going to be variable length, and we'll have to account for that in a second. But in general, this is going to be just take whatever data you want and throw at it, right? Oracle, of course, has their own compression scheme that's patented, so nobody else can use it, called OZIP. But again, the trade-off is going to be, as any compression scheme, is how fast we can encode and decode, and how good our compression scheme is going to be. So let me show you what MySQL does with InnoDB. So with MySQL, you have compressed pages on disk, and these are going to be at some multiple. The size of these pages are going to be some multiple of 8. So by default, InnoDB is 16 kilobyte page sizes, but if you compress them, it'll be within one of these ranges. So if you compress your page and it's like 900 bytes, they'll just pad it up and round it up to be 1 kilobyte, right? Pick whatever the greatest size is. And then on top of every page, in the header, there's this thing called the mod log, where it's like the write-ahead log, where you're going to record any changes that you make to the page, but that you haven't applied to because you wanted to keep the data compressed. So now if I need to access a page, just like before, my buffer pool goes out, or uses the disk scheduler, goes out and gets it from disk, brings it into memory, and it starts off in compressed form. So now if I have a write operation that wants to make a change to the tuple that's in this compressed page, assuming I have an index to tell me how to get there, then in some cases, I don't actually have to decompress the data. Like if I'm updating the login field for someone logging in on Wikipedia, I don't need to know what the old value was in order to make that right. I just overwrite whatever the old one was. So I can put a log record in the mod portion, says, hey, for this tuple, update it with this new value for this attribute. I can do much more writes to my mod log. At some point, the mod log gets full, and I'll have to decompress it and apply the changes. But for some updates, I don't have to. But now if I want to do a read, sorry, yes. It's the write ahead log. Or sorry, it's the, remember how in the LSM, we just had these like records that update this, put that, right? Same thing, right? Write ahead log is, we'll cover this later. Yeah, it's basically the operations that change the data. Yes.
Sorry, so does the mod log only exist when we have a log storage, or could you also have a mod log if you have non-log storage?
The question is, does a mod log exist only if you have log storage? No. InnoDB is not log storage, but it has it here. And we'll see this again when we talk about like a Delta store. Like, it's a common approach where you have like an area where you can put fast inserts of changes that are actually maybe applying them to the data, because that's really fast to do that, and then you have some background process fix it up. That's a common approach in systems. Yes?
So the mod log cannot exceed like the current level of size that the compressed page is.
You said the word level. Don't think of log structure storage. Just think of like every page has its own mod log, and I could put changes in there, and at some point if the mod log is full, I have to decompress and apply them and clear out the mod log. It's just a way to absorb updates to a page if I can without having to decompress it.
Is this possible to like stall some like writes when you're like writing the mod log there?
The question is, will this stall writes if I have to write the mod log to apply the mod log? Absolutely, yes. No free lunch. Yeah. All right. Yes.
Is the mod log stored on disk?
Yes. Question is mod log stored in disk? Yes. I want to keep this data compressed as long as I can. So if I'm going to flush it out, write it out to disk without applying the changes, I'll go ahead and do that. All right? Why not? Okay. So now if I have to do a read, if the read is like, go get me for this tuple, like my example, I was updating that login field where I just do a blind write without actually reading the data. If the read can be serviced by the mod log, fantastic. I just access there. But if I have to actually look what the values are inside the tuple, then I decompress it, apply whatever changes I have in my mod log. And when I decompress it, it's always going to end up being 16 kilobytes because that's the default size in InnoDB. Apply my changes to my mod log, still keep the compressed version around. Because if I didn't make any changes, maybe I don't want to, like if there was no mod log updates to apply, then why, then I can just always throw it away if I need to free a page. But the idea is, again, if I have to know something was inside of it, then I uncompress it. Yes?
Is it ever possible to have the compressed page be structured in a way to only decompress the parts you need? So let's say you want to do something to one row only, just decompress that row.
This question is there a way to have the compressed page only compress the data that you need? So in this scheme with MySQL, no. That would be choice number 2, the tuple level compression. Like I said, there's only one system that does that. You basically want to be able to do incremental decompression. gzip, Snappy, all those guys can't do that. Right? You have to sort of decompress the whole stream to jump to send any one offset. There are algorithms to do that, the tuple level one. The Terok one is the only one that I know that actually did that. I don't think anybody else does. Hold up. SQL Server can do it too, but I forget how they do it. And I don't know why they give it on by default. And I don't think they say how they do it. SQL Server in this fork of RocksDB called Terok. I can follow up on Piazza with links to that. All right, I don't want to spend too much time on this because it's MySQL and they're the ones that do it. I just want to say, like, if you want to run Snappy gzip, this is how roughly you could do it. And I actually think this is a good idea. Postgres can't do this. Right? Postgres can't do any compression except for those toast tables, those separate overflow attributes. All right. So the big thing to point out is, in this case here, the compression algorithm we're using, whether it's gzip or Snappy or zstandard, right? It's considered an opaque box to the database system. Meaning, I have a bunch of compressed bytes. The data system doesn't know anything about what those bytes actually mean. The only way it can get back to the original data is if it runs the decoder, runs the decompression algorithm to put it back into its original form, right? The compression schemes also don't understand the high-level meaning or semantics of the data, so it doesn't know, like, it should maybe pack certain pages together and compress them because they're going to be related to each other. It just says, here's the data you want to compress, go for it, and here's the output, right? So what we really want to be able to do is have our data system be able to operate on compressed data without decompressing it. So this is a high-level example. I'll show you how we'll do it in a second, but the basic idea is this. Say I have a simple table with names and salaries. I want to run some compression algorithm and convert this data into compressed form. I'm showing this with 2 tuples because it fits in PowerPoint. Always think in extremes. So what if I have 1 trillion tuples, right? I can store this now in much less space than I would if it was uncompressed. And then now if my query shows up, select star from users where name equals Andy, I'm not saying, I'm going to say how I'm going to do this yet. But what I want to be able to do is convert whatever constant I'm doing a lookup on for a given tuple, like name equals Andy, somehow convert that into its compressed form. So now, when I do my comparison, instead of comparing 2 strings, does Andy equal Andy, does Andy equal Jignesh, I'm taking whatever this XXX thing, assuming it's like an integer or something, and now I'm doing a faster comparison on those, right? And if I'm doing integer comparisons, there's instructions on CPUs to do that really, really fast versus like having to jump over bytes to do string matching. So this is the goal. This is what we want to be able to do. And because we're the database system, we can control everything. We can do this. Whereas like an off-the-shelf compression scheme can't do that. Even though they're actually going to be doing a lot of the same techniques that I'm going to talk about here in a second, like gzip and snappy, they're basically doing the same thing. They don't expose any of that to you on the outside. So they're doing dictionary encoding, but they don't expose the dictionary to you so that you can then do more fine-grained lookups. So going back here, we're going to be doing this again in the column store because now that our data within a single attribute is all contiguous to each other, they're all within the same value domain. We're going to see a lot of repeated values, a lot of values that are very close to each other, and we can exploit that in our algorithms. So here's a rough smattering of the main compression schemes, and I'll go through these one by one. Obviously the usefulness of these depends on the data set, depends on the workload. In general, the dictionary encoding one is going to be the most common. Like I think Orc, they dictionary encode everything in their files. And obviously for var length, you need these. But a lot of these other ones, if they can fit the domain you're trying to work in, you can get a big win. Much better than you can with dictionary encoding. So run length encoding, RLE, is when you have repeated values within a column. So instead of storing that value over and over again and repeating it, we're just going to store, hey, I have this value. I'm at this offset within my column. And then here's how many times it's been repeated. And I'll just store that triplet in succession rather than the original values over and over again. So obviously to make this work, you got to sort your data in such a way that you can exploit this, because otherwise you may end up ballooning the size of the compressed data. So let's say I have a really simple table that has some people information where I have some ID of the person and then a flag to say whether they're dead or not, like a Boolean flag, yes or no. So as you can see in this Boolean flag here is dead, I'm having a lot of repeated values. So what I can do is now instead of storing the original value over and over again, I'll just store some value, what offset I'm in, because that's going to help me jump around if I need to find for a match at a given offset, and then the length of the run, right? So if I have queries like this, select the number of people that are dead and the number of people that are alive, right? I can just operate directly on this is dead part here in compressed form and compute that very, very efficiently. Of course, now the challenge is going to be I have alternating values. So here we have no followed by yes followed by no. So that's the worst case scenario for us because now the size of the run is 1 for those three tuples or three values, and the size of the compressed data is actually going to be larger than the original data. So if I sort the table based on the column I want to compress, and I got to update all the other columns because I make sure my offsets match now, going across horizontally. Now you see I have all the yeses followed by all the nos, and now I can store this column as a single, or say just 2 values. All right. So this again, I'm only showing what 9 tuples here. Think in trillions or billions. This will be a huge, huge win. And we'll see in a second, we can combine RLE with other compression schemes. Like these things are actually multiplicative. I can compress in one form and then compress it again in another form. Yes. The statement is, doesn't this mess up? I don't want to have my tuple ID. This is not an internal ID. This is like the applications I have this column called ID. This is like the social security number, email address. I'm just showing ID as a simple number. All the other columns will be sorted based on whatever the columns you're sorting on. Correct, and he's right. This might be good for one of the columns, but suck for the other ones. Absolutely, yes. So how do you pick what the best sorting scheme is? NP hard. All right, next one is bit packing. So again, in SQL, you call create table. You say these are the columns I have. You have to define the data type for them, right? And oftentimes people declare things to be much larger than they actually need. Like I have like an age column, right? I'll define that as an integer. Well, that's a 32-bit integer or 4-byte integer in SQL. But if most of my values aren't going to be hitting up the max size of our 32-bit integer, I got a bunch of wasted space storing a bunch of zeros that don't mean anything for the tuples, but because they declare it to be 32 bits, I'm going to store 32 bits. So if the database system can recognize that you've oversubscribed or over-allocated the size of the amount of storage space for your data, it can actually throw things away. So if I'm storing all these values here as 32-bit integers, you see we have the original size is 256 bits, but the only data that matters is this side over here. Everything on this side is all wasted space with a bunch of zeros. So with bit packing, you basically say, I'm going to store this in a compressed form, throw away those other 24 bits, and only store the 8 bits that actually matter. And now we get this down for this example here. We go from 256 bits to 64 bits with no loss of precision. And they're all fixed length because they're all 8-bit integers. So now I can easily jump to whatever the offset is that I need for a given tuple. What's the challenge with this? What if someone comes along and inserts a value now that isn't just 8 bits, it's something larger? So this is called patching, or if you're using Amazon Redshift, they call this mostly encoding. And the idea here is that most of the values are going to be stored. I can bit pack into a smaller form. But for the outliers that are maybe too big, I just have a little special marker to say, all right, this value is actually not in line here with the rest of the values. Go jump to some patch table that will tell you what the real value should be. So if I add this large number, 99999, it doesn't fit within 8 bits. I'll store everything else as 8 bits. And then again, in Redshift, you call this mostly 8. And then I have this patch table here that says, if you scan along and find this bit sequence XXX, like think of all the bits are set to true or 1, then I know that that offset, I go look up in this table, and I find what the original value is. So in this case here, instead of storing this as 256 bits, I store all my values as 8 bits, but then I have that lookup table, which I can get down to maybe just 48 bits to store that. Yes? This question is, how do I differentiate between a value that's a sentinel to say, go look at the patch table, which is the original value? So for that one, if you set all the bits to 1, then you can't let anything be that value. You have that be special cased. Correct. His statement is, and he's correct. If you had a value that was actually that special case, then you have to store that in the patch table? Yes. But a trick you can also do is like, and here I'm showing offset 3, 999, but if you have that repeated value that's a sentinel value over and over again, you only need to store that once in the patch table. You can reuse the entry. So it's not like you need to store that repeatedly. How do you store the offsets? Just a fixed length array. Okay, bitmap encoding. For this one, instead of storing the actual value themselves, we're going to store for every unique value you have in your domain, we're going to maintain a bitmap for it. And then you just have a 1 set within that bitmap at an offset, whether the value at the tuple of that offset is that value within your bitmap. I'm going through these kind of quickly. We only have 10 minutes left. But This would be fantastic if the cardinality of the value is low, meaning the number of unique values you can have for a given attribute is low. Like my one example is dead, yes, no. Like anybody's either dead or not dead. Right? There's only two possible choices, and this is going to work really great for that. So we go back to this, right? Is dead, yes, no. So I'll maintain one bitmap for my yeses, one bitmap for nos. And as you see at the different offsets, it's either going to be 1 or 0 in either one, right? And then now if I run my queries, I can just rip through, find me all the matches where somebody's dead. I only need to scan through the is dead yes column, and I don't need to look at the other bitmap. So the original size of this was 64 bits. Assuming I can store these instead of yes no as single bits, I can get this down to 16 bits. Yes.
Why would you ever do that? Like, isn't it better to just store one bit that says 0 or 1?
The question is, why would you ever want to do this? Was it better to store is dead? In this example, yes.
But even if there's more unique values, isn't it better stored with like one number basically rather than a bunch of bit vectors?
This question is,
like if there's 4 unique values, then you just need a bit number. If there's 8 unique values, you need a 3-bit number.
Basically, should you do like something like RLE-ish? Like you saying do RLE, or there's basically store like if I have, the statement is, could you just represent the bit sequence as just a number, store the number? Yes. For 2 columns, I'm trying to show you an example. Yes.
But I just don't understand when this would ever be a good idea versus.
So question, why would this ever be a good idea? Well, if the thing you're storing isn't binary.
Well, because you're basically one-hot encoding, right?
Yeah. Well, yes.
So like, isn't it always smaller to just have like one small integer where like 0 means a value, 1 means a value, 2 means a value, and then store this directly instead of having the long sparse?
His question is, isn't it better to have a small number represent a value within my column I'm trying to compress rather than do one-hot encoding? Well, no, because I can rip through bit maps very, very quickly, much faster than I can rip through integers. Right? Find me all the even this simple example here. Find me all the. This example is not good because I could store is dead in a bitmap column.
Right. So you're saying it's easier to compare one bit than like say like is the integer equals to 3?
Correct. Yes, because there's a bunch of bit shifting tricks I can do that in modern CPUs that like I can take in a whole vector of bits and in a single instruction find all the matches versus like integers. It would take a lot more.
Even would be faster for aggregations than like accounts averages, etc. Would be faster than doing the dictionary encoding of the enum, for example.
Your statement is that bitmap would be faster. Yeah, for aggregation, yes. Again, my example here, yes, no, it's binary, so you could just store just this array here, or this array here would be the same thing as storing is dead. So I'm showing 2 examples because it fits on PowerPoint, but if you have more, it would not be a good idea. All right. Let me quickly show why it's a bad idea. So if you have a lot of columns, a lot of unique values, like the number of zip codes, then the storage space, if you just do the naive scheme, would be terrible. All right. So you don't want to bitmap encode everything. There are tricks to compress this further using called roaring bitmaps. We don't have time to cover that. Just think of like compressed bitmaps it's a way to compress sparse bitmaps. So I have a bunch of zeros, roaring bitmaps are the right way to do that, and a bunch of systems use that. All right, let me get through the last 2 compression schemes, delta encoding and dictionary compression. So delta coding, the idea is that if I'm storing values that are very close to each other repeatedly, then I don't need to store the actual absolute value for each of those measurements or whatever I'm trying to record. I just store a diff or delta from either the previous value or some global value at the top of the beginning of the page. And then now the delta I'm storing is be much less than storing the full value. So again, if I'm storing the temperature in this room at a 1-minute granularity, it's hopefully not this room, 99 would be a lot, but like if I'm recording over and again, the same temperature over and again, there aren't going to be wild fluctuations in the temperature from one measurement to the next. So instead, what I can do is or same with the time. The time's always incrementing by 1 minute. So instead, I'll just store at the top of the column some base value, and then I'll store the delta from the previous value. So now as I'm scanning along, I know how to apply those changes to get back whatever value it is that I wanted, right? So we can compress this further because if you notice in this case here, the time column, what do we have? A bunch of plus ones. So we don't need to store 1, 1, 1 all over again. We can RLE that again, and now we get the multiplicative compression where now we have plus 1 repeated 4 times. Right? Some of these compression schemes are composable. So the benefit we're going to get is the original data in this example here is 320 bits. If I just do delta encoding, I get 128 bits, but if I do RLE plus delta encoding, I can get it down to 96 bits. Again, we're talking bits here, always thinking larger scales. This will matter when you get the gigabyte and petabyte scale. In this example here with delta encoding, I have at the beginning of the page, that's the base value I'm going to use as the offset when I compute these things. There's another approach called frame of reference. And basically you have a global min value that you use across multiple pages. But the basic idea is the same thing. All right, the last one I want to get through is dictionary encoding. And the idea here is that we're going to replace frequent values that we see in our data set within a column with some kind of small fixed length integer code. And then we'll store those integer codes contiguously in memory. And then we'll have a separate data structure called the dictionary, which is oftentimes just a fixed length array. An array that we had to jump to offsets. That if I ever need to go back to the original value, I can use that dictionary to do that conversion. So typically, in most implementations, you're going to have one dictionary code per value. So if I have like a 1 megabyte block of text, I can convert that down to a single 32-bit integer. And then I have a dictionary to store that entire block of text later. You could start doing like more fine-grained things like hop encoding. But as far as I know, no system does that in production. This is also basically this is what LZ4 and Z standard and all those other compression schemes are doing underneath the covers. They just don't expose the dictionary to you. So this would be great for both doing point queries and range queries because I can rely on that dictionary to do fast comparisons on the data in compressed form without having to go decompress it. So look at a simple example like this. So here's my original data. Right? I have a bunch of integer strings that are all different lengths. So I'll then, when I compress it, I convert the name column into these compressed integers. Then I have this dictionary size structure over here that for any given value, here's the corresponding code for it. And I have a way to actually go both directions in my dictionary. So for a given code, give me the original value. And for original value, give me the code. So I need to support both operations. And this dictionary is actually be sorted based on the values that we're compressing, because now we can still apply certain comparison operators when we run queries on the compressed data and still get all the order preserving guarantees we want because the data has actually been sorted. So now I can do some tricks like this. If I have find all the users where the name ends or starts with the prefix AND, I can take my query, extract out the constant I'm doing lookup on, convert that into, or basically apply that like clause to my dictionary, which is going to be way smaller than the original data. Convert now my boundaries into to dictionary codes, in this case 10 and 20. Now in my rewritten query, I can rip through the name column with that between clause and now just do comparisons on integers, which is way faster to find all my matches. So I still had to do some string lookups, but I did that on the dictionary. And if I have a lot of repeated values, and this is fantastic because I'm not going to have to look at all the data. And then I can rip through the original data very efficiently. So this is what the order preserving guarantees of maintaining the dictionaries in sorted order gives us. So if I have a query like this, like select name from users, where name equals like AND, right? I'm still going to have to do a scan on the original table because I got to get back, I still have to get back the original value for the tuples that match. In this case here, if I have only get the distinct name, that one I only have to go look up in the dictionary because I need to find whatever that one match that I have, and then I'm done. Yes?
What if like you delete the row, you have to check like if you need to retrieve a value from the dictionary?
The question is, how do I handle deletes? How do I delete from the value from the dictionary? Deletes are easy because you could just delete the value from the dictionary and it doesn't have any gaps. Inserting is more tricky because if I have to insert something between a 10 and 11, and I don't have a value in between, I got to recompress things. The great thing about OLAP is that the data is mostly immutable, so it's not really an issue.
If you see the phrase dictionary compression, does it mean order preserving by definition, or are there dictionary compressions that are not order preserving?
The question is, if someone says using dictionary compression, does that mean by default they're using order preserving? Typically, yes. Are there compression schemes that are not order preserving? Yes, but most of them are. I just want to sort of highlight that benefit we get. Okay, we're out of time here. So I'll pick up on how we handle OTP and OLAP together next class, and then we'll have the guest speaker from Yugabyte. And then again, the recitation is tomorrow night, and then all the database company talks are all tomorrow morning as opposed to Piazza. Okay? Hit it.
Cash money, flick flips, acrobats over tracks. 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 Get the fortune, motherfuck the fame. Maintain but never strain, flow with the grain. Get the fortune, motherfuck the fame. Maintain but never strain, flow with the grain.